Let Xn be binomial with the probability Pn for all n's. So we have NP and lambda is larger than n for all n. Okay, and X is Poisson. We're going to show that the MGF of Xn converges to the MGF of X, where X is this Poisson. All right, so here in this setting, we need to think about how to, well, the strategy is basically to move from X, n, and then push it into the format of an Xn. All right, so let me just start by writing out what the MGF of, let's find the MGF of Xn. So MGF of Xn, this should be Xn of t, by definition, is the expectation of e to the t xn. Now, this is definition here of MGF. Here we're going to use, just do the expectation. And the expectation here is the sum of a, we're doing this over a binomial variable, right? That's what Xn binomial is. So starting off by e to the t, and we have little, so we're doing this over the support of Xn. So this is little xn in my notation. We could use, for the sake of simplicity, just replace Xn with k's. So k can go from 0 to n, and we're taking the binomial. We're doing not the factorial. We're going to do n over, choosing over k, and then we're going to do the Pn. So that's the probability of success, k, and then 1 minus Pn, the complement of the remainder of failures in the binomial case for each k. Okay, so this looks a little complicated, but we're now basically just following how to do the expectation of a binomial variable. First, however, I mean, the difference here is obviously this e to the tk. It looks a little cumbersome. Normally we would have just a k here, right? In the when we're not doing the MGF. Okay. So how do we proceed? Well, let's just rewrite this summation by moving this e to the tk inside this pnk, and then we're going to use the binomial theorem to simplify this whole expression. So here we're going to do the n of a k, kn, and then we're going to move in pn e to the t, all this to the power of k, 1 minus pn n minus k. And by the binomial theorem, we have now that pn e to the t plus 1 minus pn to the n is the MGF of Xn. All right, so that's the first step. Now we're going to let me put a pin here. Just say this is it. Now we're going to let me duplicate this. We're going to see what happens when we move n, when we let n go to infinity. Will this approximation, will this in this case become let's see, become a Poisson? Does this MGF here resemble, or in fact become identical to an MGF of a Poisson? So let's we're going to now rewrite, and we're going to also rely on the fact that the variable, I mean the terms inside will be inside of the this expression here resembles the compact interest limit theorem, which says let me put it here. So we have 1 plus x divided by n. This will go towards e to the x as n goes to infinity. This is the key expression that we're going to rely on here. So we need to rewrite these inner terms into this format here. And to do that, we're going to also use this information here, given to us that lambda equals np. So let me write it here and see where we can stick it in. Okay, so let's just factor out, and we can actually, one other thing here is that lambda divided by n is p, and it looks like we could, because we want to get an n, we want to get n, a bunch of n's in here, and probably a lambda. We can then see that we're going to, best strategy is most likely to replace pn with this term here, right? And we can then let n go to infinity. So it seems logical to proceed with this substitution here. So let's do that here. E to the t plus 1 minus lambda n to the n, like that. And after this, we're going to just factor out, the whole point now, strategy is to get this thing into the format of this term here. And it seems reasonable. We have a 1. Look at this. We have a 1, so that seems good. And then we have minus lambda n, which resembles this. We have also an n here. So one logical move is then to do the following, which is to do e to the t minus, and we let the lambdas be here. I mean, one thing one would want to do is to move the lambdas out, but that's not what this expression is telling us. We need the lambdas inside this parenthesis, so we let the lambdas be here, and now we are, lo and behold, we have now something that looks identical to this thing here. And therefore, when we let n in this equality go to infinity, we get e to the lambda e to the t minus lambda, which is just, now we can factor out e to the t minus 1 lambda, right? And that is, in fact, identical to the MGF of a Poisson. So that is identical. This thing here is identical to the Poisson. So this is the MGF Poisson. And that is what we were asked to complete.